Now, and it's just drop dead. Otherwise, I would probably. Don't worry, guys. It only includes five of the examples.
Okay, we're gonna start today's notes, mean value theorem. We'll spend the last maybe 15-20 minutes doing review for your quiz tomorrow. We still have to go through that fourth page on the review, so we'll do that, but want to make sure I get through the notes for mean value theorem. So we use mean value theorem to justify conclusions about a function over an interval. So let me have us. All right. Okay, so if a function is continuous over the interval, so it's got to be can't have any breaks. Okay, so bracket on a closed interval from A to B. And it's got to be differentiable on the open interval from A to B. So that means it needs to be connected from one end to the next, but then differentiable just means that the slope has to exist between A and B. So it doesn't actually have to be differentiable at the endpoints. So if I have a sharp turn at A and B, I can still go through with this mean value theorem. So bracket is for continuity, parentheses is for differentiable. Now, so this tells us that we have a smooth curve. Okay, no breaks in the graph, no sharp turns, at least not between A and B. Then there exists a point C within the open interval where the instantaneous rate of change, that's going to be your derivative, the exact slope at that moment in time, is going to equal the average rate of change. That's the slope between the endpoints. That is just slope between 2 points. Okay, so here's the formula. F prime of C is equal to F of B minus F of A over B minus A. So I'm going to have A down here. Now I have point B up here somewhere. So let's say between A and B, the graph is continuous and differentiable. There are no sudden changes in direction. And also there are no sharp turns and no places where my graph is not continuous. So whatever the slope is between these endpoints, so go ahead and draw what we think that slope is. So that's the average slope. That's the average rate of change, right? So this mean value theorem says if this is the average rate of change, let's say slope of 2 or slope of 3, there must be at least one other point somewhere along my path where I'm going to reach that exact rate of change at a specific moment. So basically, I know there's going to be another point where the slope is going to be parallel or the slope is going to be the same. That's point C. So a quick example that I think we can all kind of understand is, let's say you took a trip and that trip was 300 miles. And then you were able to complete that trip in 6 hours. what's your average rate of change? What's your average speed?
50 miles.
50 miles per hour. Does it mean that you're traveling 50 miles per hour at every moment of that trip?
No.
But can I guarantee that there must be at least one moment where I'm traveling 50 miles per hour? That's a guarantee. So that's what mean-value theorem tells us, is that if I can find that average rate of change, I know that I can locate a specific rate of change that's the exact value at least once over the course of that interval. Right. And this is rate of change, so we can think of it as slope. Okay, so here's the process. Use a function to answer the following. On the interval from 2 to 6, what is the average rate of change? So average rate of change, again, does not involve any calculus. You're just finding endpoints, and you're just finding slope. Okay, that's this piece of it. F of b minus f of a over b minus a. So let's gather our order pairs. We'll find f of 2, we'll find f of 6. So I know the slope between the endpoints is -5. Doesn't mean that that's the slope of the entire graph, but we know it's the average slope between 2 points. So basically now we can say, okay, I know the slope between the endpoints is -5. I know there must be at least one other place on the curve where the slope is exactly -5. We're looking for that point. So that's what part B is. Part B is saying on the interval, when does the instantaneous rate of change match this average rate of change of -5? So if the graph looks something like this, if there's a slope of -5 between these two endpoints, we know that somewhere along the curve must also experience that exact slope somewhere at least once. And we're looking for that point. That's what we're looking for. Okay. So we have the average rate of change. Now to get to the instantaneous rate of change, we got to get to the derivative. So what's our f prime?
-4x.
Sorry. Okay. So look at what we're going to do here. Instantaneous rate of change equal the average rate of change. And we're just setting them equal to each other, right? My average rate of change equaling my instantaneous rate of change. So in other words, I know what slope I want. Where's the location of that slope? To set them equal to each other. Okay. We don't want to insert the -5 in for the x, right? That doesn't make sense, right? We already know what slope we're after. We just don't know where that location is. So we're coming back and solving for that location. Now it says C, that's usually with mean-value theorem, we usually use that we're looking for that C value, but it's basically just the X value where my behavior is occurring, where that specific slope is occurring. Okay, so there's a distinction between mean-value theorem and intermediate value theorem. These are both common theorems that shows up on the AP exam. mean value theorem requires calculus. Intermediate value theorem a lot of times does not. So mean value theorem says, where is my instantaneous rate of change match the average rate of change? So we have to involve derivative to figure out where the slope is going to match. For intermediate value theorem, it's more like, okay, if I have two endpoints, y values, then every intermediate value between my y values of my endpoints must be reached somewhere along that graph, right? So if I start at -2, and if I end up at 5, every number imaginable between -2 and 5 is going to be touched by the graph at least once, assuming that our function is continuous. Right, so that's intermediate value theorem. It's the middle, all the middle values between my endpoints will be touched. But mean value theorem is I can guarantee a slope. Meanwhile, IVT, I can guarantee a y value. Okay, let me show you some instances of where both of these could show up on the AP exam, and we have to kind of decipher when to use which. But let's do let's look at example 2. Okay, hot air balloon is launched into the air with a human pilot. The twice differentiable function, that just means it's a smooth curve. No sharp turns. We don't know. We don't really see beyond what's in front of us, but we do know that everything between these points is going to be a nice smooth curve. There's not going to be any sudden holes or asymptotes or sharp turns. Okay. So this models the balloon's height. So at 0 minute, it starts on the ground. 5 minutes in, it rises up to 40 feet, continues rising, dips a little bit, but then at 30 minutes, it's back. It goes up to 80 feet. So between 5 and 15 minutes, must there be a time when the balloon is 50 feet up in the air? Yes. Yes, because we see my function is continuous. If it hits 40 and if it goes up to 70, or basically I can choose any value, right? I see a number above and below my target. I'm going to choose these points, but you can make an argument from 0 to 70 as well. That I must reach somewhere between 50, or I can do like 70 to, actually, we do need something involving 70 and 40, or 0 and 70. But this is intermediate value theorem, right? I can see that every value between my two y values must be reached at some moment in time. So 50 has to rise up to, has to go past 50 feet somewhere along that path. Okay, so that's IVT, right? That's intermediate value theorem. But remember that our conditions for IVT is continuity. Now, they don't say it's continuous, but they do say that it's twice differentiable, and differentiability implies continuity. So we know our function is continuous. IVT does not require differentiability. It just needs the graph to be connected, and we know it is it's fulfilling more than the condition that we need, but because differentiability implies continuity, we can say our function is continuous on the closed interval provided. Okay, this is the way that we like to write it. If my endpoint is lower than my target, and then my target is lower than my other endpoint, which is coming from h of 15, then there must be a time t where h of t equals 15. All right, for part B, between 20 and 30 minutes, must there be a time when the balloon's velocity is 1.5 feet per minute? Now, do we see anything that is velocity information that we can look at? We don't, right? But we know velocity is the what of this? It's the derivative rate of change, right? Velocity is the rate of change of position. So what we can do is, well, if the average rate of change between 20 and 30 minutes is 1.5 feet per second, then I know that there must be a balloon's velocity of 1.5 feet per minute. 1.5 feet per minute velocity at a specific moment in time. But that would require us to have a slope between 1.5. Now, the way that AP exam does it is they're not going to try to trick you and say, okay, between 20 and 30 minutes, or between 0 and 30 minutes, is there a place of velocity 1.5? And you got to try all the different options to see if you can get a slope of 1.5 to show up. Typically, if there's they are giving you the endpoints where that rate of change is occurring. Usually, I would say 90% of the time they're going to give you the points that they want you to use. So if I can show that the slope between 20 and 30 has 1.5, then I know there must be an exact 1.5 slope somewhere, or velocity somewhere along that path. So let's find the slope between 20 and 30, right? I can do change in height over the change in time. So 80 minus 65 divided by 30 minus 20. So I'll have 15 divided by 10, which is 3/2, which is 1.5. And because my average rate of change is 1.5 feet per minute, I know that by MVT, there must be a value where H prime is exactly 1.5 on that 20 to 30. Okay. But make sure that you write out your conditions. The condition for MVT is more strict. It needs a continuous statement, and it needs a differentiable statement, because if I'm trying to guarantee a slope, I first have to make sure that I don't have any sudden, things that will cause my slope to be undefined. I got to make sure that I have a clear path in my interval before I jump into MVT.
Why is it? On the question is greater, less than or equals to. It's like equals to.
Yeah, so that's something that is a bit of a kind of a subtle thing about MVT. Mean valley theorem requires that your function is continuous at the endpoints, so the endpoints has to be defined, but it does not require us to have a smooth curve at the endpoints. If my graph is this, mean valley theorem is still going to pass, because as long as my graph between A and B are safe, I can still do mean valley theorem. Okay, so mean valley theorem doesn't require my endpoints to be a smooth curve, a smooth point at that location.
Oh, makes sense.
Yeah, so but when you find your location has to be between the endpoints, because I can't if I can't guarantee a slope defined at the endpoints, my mean valley theorem is only going to be able to guarantee a value between the endpoints. So it's bracket for continuity, parentheses for differentiability, and then the location that I'm looking for has to live between the endpoints as well. So those are kind of just subtle things about mean valley theorem. Okay, so we see the distinction between IVT and MVT. IVT, you're looking for a specific, trying to guarantee a specific value that is given to you, and then mean valley theorem is asking about the rate of change. Can I guarantee a rate of change off of that data? Okay. Let me skip a few of these because we'll come back to it, but I want to kind of hit the main points. Let's go to the next page and talk about Rolle's theorem. So Rolle's theorem is a mean valley theorem, but it's very specific. Rolle's theorem says if my function is continuous and differentiable, and my endpoints are the same y value, then there must be at least one other point where the slope of the tangent is going to be 0. So let's convince ourselves of that by looking at this picture here. So let's say I have a graph that is continuous, right? No breaks, no sudden, no sharp turns, no points, no sharp points. So continuous differentiable, but then my endpoints happen to have the same y value. So what is the slope then between my endpoints? Zero. So what this tells me is that somewhere along my path, there also must be a slope 0. Right? I'm not able to guarantee if it's a max or a min, but at least I can guarantee that slope 0. But it's basically mean value theorem, right? Because if I have f of a equals 3 and f of b equals 3, 3 minus 3 over is 0 over 3 or 0 over something, and that's 0. I'm still doing the same thing. I'm still plugging in 0 into my derivative and solving for x. It's just that we have a special name for a slope 0 and we call it Rolle's theorem. So it's just a very specific case of mean value theorem. And also because the slope that we're looking for a lot of times is slope 0. So we just created a specific name for looking for slope 0. All right, let's look at example 2 just to kind of show you that those steps. All right, determine if Rolle's theorem can be applied for our function on the interval from 1 to 2. If so, find the value of c such that f prime of c is equal to 0. So first things first, we have to check our conditions. Is our function continuous and differentiable? Yes. It's a polynomial, right? Polynomial is going to be safe all the way through. We just have to practice writing out our condition. Again, continuous condition is with brackets. Differentiable condition is with parentheses. Now, remember with Rolle's theorem and mean value theorem, find the average rate of change first. If you find the derivative at the beginning, it's going to potentially throw you off. I see some students do this. They find the derivative. They find the derivative. And then they start plugging in the a and b value into the derivative and then find the slope off of that. And then that is going to throw everything off, right? Then you're doing f prime of 3 minus f prime of 1 over, and we never want to do this. We never want to plug in the value into the derivative. So I feel like if we can just remind ourselves, let's get the information from the function side of things, get that out of the way, and then move on to the derivative. That way we're less tempted to want to involve plugging in these endpoints into the derivative when that's not part of the process. Right? We don't care about the slope at 1 and 2. We want to find the average rate of change between 1 and 2. So let's find f of 1 and f of 2. F of 1 is equal to 0. 1 minus 3 is -2. -2 plus 2 is 0. F of 2 is equal to also 0. Now, I know they're showing you the same y value. We can already say this is Rolle's theorem, but I want to also show you, right? If I were to subtract my y values, changing y over changing x, I'm still going to get 0 because my y values are the same. So they must equal 0. Now, do these have to be equal to 0? As long as they are what? The same. Yeah, as long as they're the same. Now, if you just want to go through mean value theorem and just do fb minus fa or b minus a, that's fine. Then you kind of just same process. We should have a special name for slope 0, and that's Rolle's theorem.
You have to like mention the special name.
No, you don't have to. But if they mention Rolle's theorem, just know what that's referring to, right? Now, if this was a different slope, let's say a slope of 1, slope of 3, that would be fine for mean value theorem, but it won't be good enough for Rolle's theorem. Rolle's theorem is looking for a slope 0. So if I can't show a slope 0 between the endpoints, it would break down for Rolle's theorem. Okay. Now we can find the what? Derivative. And then you're going to set your instantaneous rate of change equal to your average rate of change. Set them equal to each other, solve for x, and we can find somewhere between 1 and 2, there must be at least one other place on the curve where the steepness of my curve is exactly 0.
You're required to write it as C equals or.
You don't,
Oh,
yeah, if they mention it, then yeah.
Okay.
And also that's the typical what do I want to say? It's typically what they use when they talk about mean value theorem, Rolle's theorem. They use C value for some reason. So
same thing for limit sec.
yeah, limits x approaches C. Yeah. All right, definitely want to come back and revisit this, but I want to just introduce you to the process, right? You find your average rate of change, find the slope between the endpoints, find the derivative, and then just set them equal to each other. Yeah. Yeah, if you were to write a statement, it may look like, yeah, we'll do some more tomorrow, but something like this where, by MVT, now all your work, you can just show, it has to be in one statement, not as messy as IVT. You say that by MVT, there must be a value where H prime is equal to that value between 20 and 30. Let me see if I can find a better example. I don't know if there's a set way of writing something for mean value theorem, but I think the graders do want to see that you understand that we're connecting average rate of change with instantaneous rate of change. And if we can just be able to demonstrate that there's a knowledge of that connection, we can word it multiple different ways. Yeah, so yeah. But yeah, we'll definitely do more mean value theorem and Rolle's theorem so that you guys can obviously get more comfortable with what's a way that we can phrase it that will show that we understand the logic behind. Okay, let's go to our quiz review, page 4, and this is the extended problem with diagonal theorem, area, and trig.
When is the homework your kids do?
Wednesday. Okay, in your packet, last page. Number 9, I believe. Part B, the angle theta is a little vague in terms of where that theta is. So the theta is going to be there in that corner. And on the quiz, I'll draw the diagram for you so you know where that theta is. But for now, just know that that's where theta is. Okay, so go ahead and set up your diagram. Person X, person Y, walking on straight paths. Y travels south. And then person X travels east, moves away from the intersection. Right, does everyone have this packet? And y is the vertical component of your triangle, x is the horizontal component. Pythagorean theorem. Notice that dy dt is a -2, not because it's going south, because that y value is decreasing over time. So happens that at this moment in time, dc dt is 0 meter per second. That doesn't mean that dx dt is not changing over the entire course. Just at that specific moment, things line up in a way where dc dt is not it's equal to 0. Okay, any question with A? Okay, part B says find the rate of change of theta. Do we have a side that we can take advantage of in terms of a side that is a constant? Is there a side that is not changing over the entirety of the problem?
B side.
Z is changing, it's just at this moment in time, it's not changing. So
Change.
they're all changing, right? They're all changing, right? So as the person is walking, both y is decreasing, x is increasing, and z is eventually going to be increasing as well. There is no constant, which means that there is no one or two trig that is better than the other in terms of avoiding quotient rule. Here, we kind of have to go through quotient rule. So any trig function we can use, but I'm going to use tangent because the information is given to me in terms of x and y. So that's where I decided to start. Okay, now you could use sine, you can use tangent, you can use cosine, because you have everything that you need to use any of those derivative, and use any of those trig equations, because you have all three sides and all three derivatives. But I'm just going to rely on the original variables. That's where I have initial information about. So if I want to find the derivative, what does tangent become? Question.
Oh, how do you know when you're setting up your trig function, if you should just leave it to variables as y and x, or if you should plug in?
Yeah, you're going to have to kind of visualize the problem and convince yourself, is is the sign staying constant or is it changing over time?
Okay, so if it's changing, then just put in the.
They gotta keep it variable, right?
Okay.
Now, the previous problem that we did where a person is standing here and then there's a launch of the rocket. And we know this part is not changing, and so we know we can put a number here because we know that's never changing, right? But yeah, if you convince yourself that length is changing over time, you have to make sure you put a variable there to begin with. Now, after the derivative, then you can start putting numbers in, but we don't want a number to represent that length if it is not going to stay that value the entirety of the problem.
What about like the ladder problem where the length never changes, but I still remember like.
That's right. I put a Z there, but you can get away with putting 25 there and be okay.
But then that derivative would equal 0, like, would it mess everything up or?
Not necessarily. Let's say this was X and Y and this was 25. And if I want to use tangents, or if I want to use sine, I would do sine of theta is equal to Y over 25. I can avoid quotient rule. I still got to go through power rule. It would zero out within quotient rule, but there's still a derivative there, right? It's not going to be zeroing out.
Okay.
Okay, yeah, so, I mean, I personally, I wouldn't go through quotient rule. But I would find this to be easier to just do 1 over 25 times Y, just do power rule. Make this 1 over 25 dy dt.
And then if you did Y over C, you'd still get the same thing, or?
If you did Y, oh, you mean Y over C, yeah, if you did Y over Z, you still get the same thing, yes. But it'll feel a little messier, but eventually the dc dt will wipe
I just have
everything out.
to plug it back in eventually, right?
Exactly, yeah. So yes, you can leave everything as a variable if you want, but eventually you'll catch yourself knowing a portion of it is a constant and things will wipe out the way it's supposed to wipe out. Okay, let's go through this process again. Tangent theta becomes what? Times d theta dt. Good. And then the right side quotient rule, right? F prime g minus f g prime all over g squared. So remember the thing that is unique about the trig related rates process is that okay, obviously we're looking for d theta dt. We have everything that we need on the right side, but what to do with that secant squared theta? You're not going to find theta. You're going to find the entire ratio that replaces secant of theta. Right. So the way to go about this process is, for me, I like to just draw another triangle so that it doesn't, so I don't have a ton of information off that first triangle. I just want to build the triangle with that moment in time's values. So this particular moment in time, X is 20, Y is 10, and Z is 10 root 5. And if I can have this in front of me, I can figure out what secant and theta is. Right? Secant is hypotenuse over adjacent. I get that ratio to show up, and that is what I put in for my variable, my secant theta. So everything on the right side is ready from part A for us to use. The unique thing about this process is we got to find a value to replace that secant theta. I have root 5 over 2 from the triangle. I square that expression, I get 5/4. Divide both sides by 5/4, the same thing as multiplied by its reciprocal. And then your d theta dt is always radian per time unit. Okay, any questions with this process? All right, part C. How fast is the area of the right triangle changing? What's the area formula for right triangle? 1/2 x, 1/2 base times height, 1/2 xy. Yep. Right. And if I want to find the derivative, I gotta go through what? Product rule, yeah. I'll move to the top once you guys, anyone's still looking at part B.
What if they ask for like the second derivative or something? Like, there was like a problem before this that asked for the second derivative. It said, at that moment, like, is the rate of change increasing? I don't know, like.
Yeah, I won't quite give that to you on the quiz, but we know that because we have DHDT, the rate of change increase decreasing must involve the second derivative from that DHDT. So we just do the derivative again. It's just,
And then plug in.
yeah, and then plug in the information that you've gathered from before. Okay, here's part C. If you're ever struggling with your units of measure, look at the variables involved and then just find their respective units and then just put them over each other. Area is a two-dimensional unit, so square meters. Time is seconds, so square meters per second. Okay, so tonight's study over your review sheet, but it doesn't have everything on it, so look on what I've gathered here. These are all the relay race problems that you want to make sure that you're comfortable with, and then I think over the course of the homework, the class, the packets, and the AP problems, all of these are covered. I will have a morning review at 7:15 to go over any problems either from the packet or homework or any type that you want me to go over. I can go over that tomorrow morning. I'll send you guys a link to remind if you want to join virtual on Teams. Okay, come get your phones. Yes. Velocity increasing, decreasing is talking about acceleration. Increase, decreasing speed, you got to compare size to velocity. Oh, that's the one takes into account the direction. Yes. Well, this we know is just acceleration. We talked about how increase, decrease in size would mean the size would be the same.
No, but no, that's something. Yeah. I think that, I said.
All right.
Yeah, the math.
Oh, that.